Okay, in this video we're going to look at rational functions, kind of from a college algebra perspective. Um, we're going to practice graphing them, finding asymptotes, and a little bit of finding holes. So this is based off of the OpenStax book loosely, and so if you want to get more detailed descriptions, go check out the OpenStax college algebra textbook. So a rational function y equals f of x is of the form p of x over g of x, where p of x and g of x are non-zero polynomials. How to find the domain is we solve the denominator not equal to 0, so we don't want to divide by 0. So that's how we're going to find the domain. If we're looking for the y-intercept of a rational function, we're going to plug in x equals 0, provided that x is equals 0 is valid in the domain, and then solve for the y, and then we're going to write as an ordered pair 0 comma b, whatever the result is of evaluating the polynomial, the rational function at 0. In other words, that's p of 0 over g of 0. You're just plugging in 0 in for all the x's. Okay. The third thing we're going to look at is we're going to figure out how to find the x-intercept. So basically what you're going to be doing is you're going to be solving the top equal to 0, and you're going to write that as ordered pair or pairs depending on how many x-intercepts you have, a comma 0. The reason why it's only the top equals to 0 is you can clear the fractions by multiplying the top and the bottom by g of x, and so that'll leave you with p of x is equal to 0. Of course, what we're going to want to do is factor and reduce the polynomial before we do this. So we want to factor and reduce first. So we want to factor and reduce before we do this, okay? And so I didn't have enough space, so we're going to move on to the next slide here, and we're going to talk about x values of holes, and vertical, horizontal, and oblique asymptotes here. Okay. So x values of any holes. So if we take a rational function, factor the numerator and the denominator, and we have a common factor that we can divide out, such as the one on the screen here. You have f of x is equal to x squared plus 4x plus 3 over x squared plus 6x plus 5. We can factor the top and get x plus 3, x plus 1, and factor the denominator and we get x plus 5 and x plus 1. So we have a common factor of x plus 1, and that's going to divide out, and the root of that factor, x plus 1, is minus 1, and that's going to be a hole in the graph. Now what you have left in the denominator is an x plus 5, so if we solve x plus 5 not equal to, well, I guess we can say equal to 0, then x equals negative 5 is going to be our vertical asymptote. So vertical asymptote, vertical asymptotes, after you've factored and reduced, where the denominator is equal to 0 is a vertical asymptote. If you have a factor that reduces, it's going to be a hole. So we can't have, it's either going to be a vertical asymptote or a hole. Now both x equals, or x is negative 1, and what is the other value? Negative 5. Those are not in the domain. So holes and vertical asymptotes are never in the domains. So when we look at the domain, we're not going to reduce. We'll figure out our restrictions first, that being negative 1 and 5. Because the factor of x plus 1 divided out, that's going to be a hole in the graph, and because the x plus 5 remains, the root of that factor, which is negative 5, is going to be a vertical asymptote. Okay. Now, horizontal asymptotes, there are 3 cases depending on the degree. So the degree of the bottom larger, so the first case, we're going to have HA abbreviated for horizontal asymptote, y equals 0. And so, for example, I have x squared plus 1 over x cubed minus 4x plus 2. The degree of the top is 2, and the degree of the bottom is 3, and so that's going to have a horizontal asymptote of y equals 0. Sometimes students refer to that as bottom heavy. Okay, if you have a tie in the degree, so if the degree of the top and the degree of the bottom are the same, then the horizontal asymptote is going to be the quotient of the leading coefficients. So I say y equals a over b, and so we have an example there. Y is equal to 2x plus 5 over 3x minus 1. So both are degree 1, the top and the bottom. The leading coefficients are 2 and 3, so we have a horizontal asymptote of 2/3. Now, if the degree of the top is larger, you're not going to have a horizontal asymptote. Okay, so you won't have a horizontal asymptote. And looks like my number is not the best. That should be 7. Oblique or slant asymptote, so sometimes it's referred to as an oblique or slant asymptote. If the degree of the top is exactly 1 larger than the degree of the bottom, then the rational function has an oblique asymptote. To find the oblique asymptote, perform long or synthetic division, and the quotient will be the oblique asymptote. We won't care about the remainder over the divisor. Now, horizontal asymptotes and oblique or slant asymptotes are going to be described as end behavior as x gets larger, so x goes to positive infinity, or when x gets very far into the negative, so off to the negative infinity, we can talk about some sort of behavior. So I'm going to hop to the end of the video because I wasn't able to insert a new slide, but I've made a spreadsheet that kind of gives us a little bit more insight and I picked on this function right here. So I'm going to run all the way to the end of the show here. So there it is. So here's our spreadsheet, and I have the rational function right here, x squared plus 4x plus 3 over x squared plus 6x plus 5. And so we did have that factored. We had it factored as x plus 1, x plus 3, and divided by x plus 1 and x plus 5. So I'm going to be interested in a couple of things. Probably the first thing we're going to look at is this does reduce down to x plus 3 over x plus 5. And so I'm going to be interested in what happens when we get close to minus 1. So you see, getting close to minus 1 here, what's happening to those y values? So here we're getting close to minus 1, so what's happening to these y values? So if I look at the 2 points closest to minus 1, the negative 1.001 and the negative 0.999, they look about close to 1/2. They look really close to 1/2. And so I'm going to have a hole at probably 1/2 and negative 1. Now it turns out that if we evaluate the reduced fraction here at minus 1, so minus 1 plus 3 over minus 1 plus 5, that's going to give us 2 over 4, which is exactly 1/2. And so we can use the reduced form to actually find the y-coordinate of the hole. So here we're going to have a hole at negative 1/2 and I'm sorry, I'm getting it mixed up here. Let's start over. We're going to have a hole at negative 1 and then 1/2. And then what that's going to look like on the graph, it's going to look something like that. That would be a hole in the graph. Okay. If you're moving on to calculus and further, we would call this a removable discontinuity. We just have one little hole in our graph there. Okay. Now, I'm also interested in where the denominator is equal to 0 after we factor and reduce. So I'm looking at the denominator there, x plus 5, and the root of that is negative 5. So I'm going to explore what happens around negative 5. So I pick values close to negative 5 on the left and on the right. Now I chose minus 5.1, negative 5.01, negative 5.001, and notice that as we get closer to negative 5, this is big. This is a big positive, and this would be big negative, and I made big absolute value. So what's going to happen here is if we're approaching minus 5, on one hand it's getting very large, on the left-hand side, and on the right side it is getting very small there. And that's characteristic of a vertical asymptote, where we get closer to that particular value, this value being -5, that the y values get very large positive or very large negative. And what I mean by large negative, I mean the absolute value is very large. Okay, so that's a little bit about holes in vertical asymptotes. You can read some more about it in the OpenStax textbook. Now, over on the other side of our spreadsheet, I've done the same thing. I've used the same function, but now I'm looking at the end behavior. What's going on with the end behavior? And so you do have an x squared over x squared, and so this is a degree 2 over degree 2, so this is a tie in degree, and the leading coefficients on both of them are 1. So you're going to have a horizontal asymptote of y equals 1 over 1, which is 1. Now, as I get further and further off in both the left and the right hand directions, as we get further to the left, going off to negative infinity, we have negative 1,000 as the x value, and the y value looks pretty close to 1 to me. And then if we get very large in the positive direction, like going off to positive infinity, here's 1,000, I'm sorry, it's 10,000, and you see we have 0.9998, which is very close to 1, and so that's kind of our reasoning for some of these horizontal asymptotes. So this is only the case where we have a tie in degree. We can do similar arguments for the other cases here. And so we're going to take a number of functions. I think we're going to do 4, and we'll talk about how to find all the information. So find the domain, find your intercepts, find vertical and horizontal asymptotes or slant asymptotes, and any holes. So we'll talk about how to find all of that, and then we're going to use that information to actually graph some rational functions. So we're going to go back and hop back to that first or second slide. So here we go. Okay, so here we are. So we had a little bit more in-depth discussion about holes and vertical asymptotes, and a little bit of discussion about horizontal asymptotes. And so let's go ahead and work through a couple of problems, getting all the parts together and using that to graph it. So the first function we're going to look at is, what do we have? 3x minus 1 over 4x minus 8. There's not much to factor and nothing to reduce, so we'll go ahead and find the domain. So if we're going to try to find the domain, that's setting the denominator not equal to 0. And when we do that, our only restriction here is 2. So our domain is going to be all real numbers except for 2. Now, oftentimes when I find the domain, I'm finding the vertical asymptote at the same time if I don't have any factors that reduce, which will most of the time be the case. Won't have very often will we have holes in our graph. Okay. The second thing I have on our things to find is the y-intercept. And if we're going to look for the y-intercept, that means the x is 0. So we can just plug 0 in. And 3 times 0 minus 1 over 4 times 0 minus 8. And so that's going to give us 1/8. And if you want, you can convert that into a decimal. It might be a little bit easier, so 0.125, that's going to be pretty close to the x-axis. For the x-intercept, that means the y, or the fx, is equal to 0. So 0 is equal to 3x minus 1 over 4x minus 8. Now, on the description, previously I said, well, it's really only when the top is equal to 0. So if we multiply both sides by 4x minus 8, on the left-hand side you got a 0. So 4x minus 8 times 0 will be 0. And on the right-hand side, the 4x minus 8s will be absorbing, and you have precisely the top equals to 0. Okay, so that is our little bit of a shortcut. So if we have a fraction equal to 0, that happens when the numerator is equal to 0. So 0 is equal to 3x minus 1. Solving that, x is going to be 1/3. As a decimal, it's about 0.3. Okay, so it's going to be 0.3 and 0. I don't know why I put 1 there. 0.3 and 0 as our x-intercept. The next thing we're going to look at is any x values of holes. And because we had no factors that reduce, we don't have any holes. If you're doing the homework online, it's going to want you to say, if there's no holes, you're going to say DNE, or does not exist. Okay, so no holes. Okay, we will find a vertical asymptote. So after you factor and reduce, when the denominator is equal to 0 is a vertical asymptote. So there was nothing to factor and reduce. We just solved the denominator equal to 0, and we already did that when we found the domain. So what makes the denominator 0 is 2. So vertical asymptote at 2. Part F, we're going to find the horizontal asymptote if there is one. The degree of the top is 1. The degree of the bottom is 1. So it's going to be a tie, quotient of the leading coefficients, and the leading coefficients are 3 and 4. Okay. Now with our rational functions, they will either have a horizontal asymptote, a slant asymptote, or neither. They will not have both a horizontal asymptote and a slant asymptote or oblique asymptote, and they will only have one. They won't have two slants. They won't have two horizontal asymptotes. They may have multiple vertical asymptotes though. Okay, and so letter G, no oblique asymptotes or slant asymptotes. And again, you would say D and E if you're doing the homework online. Okay, so I've taken a screenshot of an XY plane there, and we're going to go ahead and start graphing some of our information. So we do have a vertical asymptote at x equals 2, so we'll draw that as a dashed line. And then we do have a horizontal asymptote at y equals 3 over 4. Okay, now the asymptotes really determine the behavior of the graph. So there's two possibilities on the left-hand side of the vertical asymptote. We can be up like this, or we can be down like this. So those asymptotes are going to determine the behavior of the graph. Okay, now because I have a y-intercept at, what is our y-intercept at? 0 and 1.25, and I also have an x-intercept at about a 1/3, so those are going to be like right here. So it's actually going to be like this lower graph there. So I got enough information there. If you want a more accurate picture, you can certainly pick more points. We're looking for rough sketches right now. Now on the other side of the graph here, again, will either look like this or will look like this. Okay, and it's going to get nice and close to those asymptotes. Now I know it's not the bottom one because I don't have an x-intercept over here. We only have one x-intercept and it's at 1/3, so that rules out that possibility. You can sometimes cross horizontal asymptotes and slant asymptotes. You will never cross vertical asymptotes because vertical asymptotes are not in the domain. Okay, so let's go ahead and install some of our points. So we're going to install our x and y intercepts. So maybe not the best. So you just gotta maybe zoom in or whatever. So there's our x-intercept at approximately 1/3 and 0. And here's our y-intercept at 0 and 1.25. So those 2 points are there, and that's enough information to do a rough sketch of the graph here. So there it is. Okay. Now on the right-hand side of the graph, maybe I want to pick an extra point to help reassure everyone that it is in the upper half of that vertical, upper half on the right side, I guess I can say. So let's pick a point out there. So let's pick, I don't know, 5. And we're going to plug it in the formula. And we're going to get a y value from that. So we get 14 over 12. So that's approximately 1.3. So we're looking at the 0.5 and 1.3. So I've gone ahead and sketched it there. That should be enough, but we can certainly do another point. So maybe we want to do 3. 3 times 5 minus 1 over 4 times 3 minus 8. So that's going to give us 8 over 4, which is 2. So we can sketch that point too. And so now you have 2 points. That's probably enough to do a rough sketch. Okay. we need calculus to get a better picture here, but or plot more points. So this is good enough. Okay, so we kind of want the general shape of the graph. Where are the intercepts? Where are the asymptotes? That's what we're looking for. Okay, and when in doubt, you can always plug in more points. So maybe you could plug in 6 and 7 and 8 all the way out to 10 if you need to kind of get a better idea of what the graph's looking like. Okay, so we're going to look at another example here. At least I think we're going to. Okay, here we go. So we're going to look at, this time, f of x is equal to x squared minus 5x plus 4 over x minus 6. Okay, now I'm going to go ahead and do this part now. We'll go through and find all the domain and all that other stuff too. The degree of the top is exactly 1 larger than the degree of the bottom. So the degree of the top is 2. The degree of the denominator is 1. So that's going to tell us we have a slant asymptote. Because the denominator is a linear factor, we can go ahead and use synthetic division. Okay, so we're going to do our synthetic division. Bring down the 1. 1 times 6 is 6. Negative 5 plus 6 is 1. 6 times 1 is 6. And an add, and then we get a remainder of 10. So f of x can be written as, we'll say it's y for now. Y equals 1x plus 1 plus your remainder over your divisor, okay? Now, when we look at this right here, the degree of the top is 0 and the degree of the bottom is 1, so the degree of the bottom is larger. So this is going to end up going to 0 as x goes to infinity, or negative infinity, so plus or minus infinity. And so the characteristic of the graph is going to look like y equals x plus 1, so that's what we call a slant asymptote. So if you imagine large values of x being plugged in there, like 1,000,000, so 10 divided by 1,000,000 minus 6, so that's going to be 10 divided by a huge number. That's going to be really small. It's going to be basically 0. Same argument for a big negative number like negative 1,000,000. So 10 divided by negative 1,000,000 minus 6. It's going to be incredibly small. So it's going to take on the characteristic of y equals x plus 1. So we're going to go ahead and do all that again, but there's a little bit of an argument for the slant asymptote. So it works a little better when we get into calculus and we can talk about limits and whatnot. So that is our slant asymptote. So that's an end behavior type of thing. As we go off to positive and negative infinity, the graph is going to look very similar to y equals x plus 1. All right, so let's go ahead and we'll find the domain, and that's finding the restriction. So x minus 6 can't be 0, so x cannot be 6. So it'll be minus infinity to 6, union 6 to infinity. We'll go ahead and factor x minus 4, x minus 1, all over x minus 6. There are no factors that divide out, so there are no holes. And 6 will be our vertical asymptote. Part B, let's find that y-intercept. So we're going to plug in 0 in for the x. So we'll go ahead and do that. And so that's going to be negative 2/3. So 0 and about 0.7 if I round a little bit. So 0 and about negative 0.7. The x-intercept is where the top is equal to 0. And so we're going to say x minus 4 equals 0 and x minus 1 equals 0. So that gives us x equals 4 and x equals 1. So we get 4, 0, and 1, 0 as our x-intercepts. Okay. Part D, there are no holes, nothing factored and reduced. So you would also add in, D and E. Okay. So you'd say D and E if you're doing the homework online. Vertical asymptote is where the denominator is equal to 0 after we factor it and reduce. So that's going to be x equals 6. Horizontal asymptote, there is none because the degree of the top is larger. So the degree of the top is larger, there's no horizontal asymptote. and so you would say D and E. But we do have a slant asymptote because the degree of the top is exactly 1 larger than the degree of the bottom. And we'll do our synthetic division again like we did at the beginning. And it looks like I did a better job the first time, so I think 4 plus 6 is 10, not 12. So we don't care about the remainder when we're talking about a slant asymptote because we're talking about end behavior, so that's going to be y equals x plus 1. Alright, so we have put in a xy plane, and we're going to put in our vertical asymptote of x equals 6 as a dashed line. We will also put in our slant asymptote or oblique asymptote as a dotted line. Y-intercept is 1, and then we're going to go up 1 over 1 as our slope. So we're going to go ahead and draw that in. Okay, and we can start putting in our intercepts. So about negative 0 and negative 0.7, we'll put in that y-intercept. Put in those two x-intercepts, and so this graph here, we're going to look on either side of the vertical asymptote. So we could be up here, or we could do something like this. Okay. Now, because I have all those points right here, it's going to be the lower branch. Okay. Now, on the other side, it's either going to do this, or it's going to fit up in between these asymptotes here. And I actually have enough information to tell you that it's this one up here because I don't have an x-intercept over here. Okay, but I'll show you what you can do if you're still not quite sure. You can just pick some more points, and we'll do some of that in a little bit. Okay, so I got those 3 points, so we're going to be flattened out to our slant asymptote, and we'll cross those points there, and then all the way down, approaching that vertical asymptote as we approach 6 from the left-hand side. So I'm going to go ahead and pick a value on the right-hand side of 6, okay, on the other side of the vertical asymptote there. So I'm going to plug in 9. I can plug 9 into the original, or I can plug 9 into the factored form. It doesn't matter. It's going to give me the same number. So I plug that in, and I'm going to see what my y value is. And my y value is 40 over 3, which is about 13.3. And so that's going to be a little bit up there. That's all right. We'll go ahead and do our best here. So that's our point there. We can extend the asymptotes a little bit, and so we kind of get that little piece up there. And not every graph is going to fit on a nice 10 by 10 grid there. So that's our slant asymptote, and that's our graph there. Okay. All right. And I think I pulled up Desmos, and I did another. I used it to graph it. So here's what it looks like. Okay, so here's your slant asymptote, your vertical asymptote, and we were able to do a pretty good job. Here's that 0 and 0.7. Here's 1. And here's 4 as your intercepts, okay? And we found 9 and 13.3, so somewhere up there. So that's what we ended up finding. And certainly you can pick more points if you want to get a better idea what this looks like. Because I had that point right there, that was enough to tell me what the graph was doing there. Okay, so what are we on, number 2? So we got 2 more to look at. Try to go through kind of the different possibilities. So we're going to look at another one here. So this time it's going to be f of x is equal to 2x plus 8 over x squared minus 9x plus 8. So this one requires us to factor to establish what the domain is. So we're going to go ahead and factor both the numerator and denominator while we're at it. Nothing's going to reduce, so no holes. The domain is where the denominator can't be 0, or everywhere where the denominator is not 0, or is finding a restriction. So x minus 1 and x minus 8 can't be 0. So that gives us 2 restrictions of x can't be 1 and x can't be 8. So the domain will be everything but 1 and 8. Okay. And then we'll go grab that y-intercept. So y-intercept is where the x is equal to 0. And so our y-intercept should be 0, 1 here. Yep, 0 and 1. X-intercept is where the numerator is equal to 0. So 2x plus 8 is equal to 0. We'll subtract 8 and divide by 2, and we get x is equal to negative 4. Okay, so we get negative 4, and 0 is our x-intercept. Okay. Nothing factored and reduced, so we do not have, and in terms it has to have an x in it. So we have no holes. There are no holes in the graph. So we say does not exist. And then we'll look for vertical asymptotes. And so if we found the domain, usually we find the vertical asymptotes too. So vertical asymptotes where the denominator is 0 after you factor and reduce. That's x equals 1 and x equals 8. So we have 2 vertical asymptotes. You can only have one slant or horizontal, but you can have multiple vertical asymptotes. Okay. There is a horizontal asymptote. The degree of the top is smaller than the degree of the bottom. And if we want to get a little bit fancy, I can try to give you guys an argument. I won't write in red, though. So we have 2x plus 8 over x squared minus 9x plus 8. And so I can factor out, let's do it this way. This will be a little weird. I'm going to factor out an x squared, 2 over x plus 8 over x squared. You can verify that's true by distributing that x squared. Factor out an x squared out of the bottom. Okay. Now as x gets larger, well, let's first absorb the x squared. So those are going to absorb. As x gets larger, 2 divided by a big number and 8 divided by a big number squared, those are going to be 0. And the same can go with these parts here. So essentially you're going to have 0 on the top and 1 on the bottom, which is 0. And so that would be our argument for the end behavior approaching 0. And you can do a table like I did, or you can plug in big numbers. You know, plug in like 100 and negative 100 into the formula and see what your y values look like. And to convince yourself that the horizontal asymptote is y equals 0. Okay, so horizontal asymptote, y equals 0. Because it has a horizontal asymptote, you cannot have both a horizontal and an oblique asymptote. So no oblique asymptote, so we can say that does not exist. Okay. Alright, so we'll put in our xy plane. And we're going to put in our vertical asymptotes, x equals 8 and x equals 1 as that dashed, if I can say it, dashed lines. Okay. All right, and then we have a horizontal asymptote, but y equals 0, so we'll go ahead and put that in also. And then we'll also put in our x and y intercepts. So we'll go ahead and put those in. Now, here's what can happen. I can be mostly below, like that. I don't have a y-intercept down there, so it's not that. And we have those 2 points, so it's probably going to look something like this. Okay. So sometimes you can cross your horizontal asymptote or slants. You cannot cross the vertical asymptote because that's where the denominator is equal to 0. Okay. Then we have a big mystery what happens here. And probably the best thing to do is pick some points to see what's going on there. And then on the other side, we might be up here or down here. I don't know. So I'm going to pick a point out there. Okay. So we do have those 2 points, so that's enough to give us at least this part of the graph. And you can cross horizontal and slant asymptotes sometimes. It happens. Okay. All right. And so the big mystery is in the middle there. So let's clear up some space, and we'll pick some points, maybe 2, 4, and 6. Those might be good enough to kind of get an idea of what's going on inside between the 2 vertical asymptotes. And there's other ways of going about doing this, but this is probably the easiest. So we're going to plug in 2. You can do it in the original form, or you can do it. Pardon me. You can do it in the original, or you can do it in the factored form. I think it's easier to do the computations in the factored form. So we'll go ahead and do that. And that's going to give us minus 2. So that's going to tell us we're going to be entirely below now. There's no x-intercept over there, so we have to be entirely below. So we might have something that looks like a parabola. Okay, so we got that point there, 2 and negative 2. So we'll plot that point. Well, we were going to pick 4, so we're going to plug 4 in, work it out, and get a y value. So 16 over 3 times negative 4, so that's going to be about negative 1.3. So we're going to plot that point also for negative 1.3. And then we'll also plug in 6, so we'll try plugging in 6 to get another value. And that's going to give us about negative 2. And so we got those 3 points there. And so probably we have some sort of, kind of like a parabola down there. Okay. And if you want to get a better shape, pick more points. Okay, and then we need to pick a point out past 8 to see what's going on. So maybe we'll pick, I don't know, 9 might be a good value. So pick 9. We'll plug that in, 26 over 8 times 1, so that's about 3.25. And so that's going to be above, so that tells us enough there. It is not going to cross the x-axis because we don't have any more x-intercepts. We only had 1, and it was over here. Okay. We're going to look at one more example here, and this one's going to have a hole in it. So this one's going to have a hole in it. We have f of x is equal to x squared minus 6x plus 8 divided by x squared minus 5x plus 6. We'll go ahead and factor it. The top factors into x minus 2 and x minus 4. The denominator factors into x minus 2 and x minus 3. Okay, I am not going to reduce yet because I want to make sure I get my domain correct. So yes, the factor of x minus 2 absorbs or divides out or reduces, whatever you want to say, but 2 is a restriction. So for our domain, it is going to be all real numbers except for 2 and 3. Those are going to be our restrictions, 2 and 3. So minus infinity to 2, union 2 to 3, union 3 to infinity. Okay, now I'm going to go ahead and reduce, and we have x minus 4 over x minus 3 for everything but 2. Everything but 2. Okay, part B, we're going to plug in 0 in for x. I can use the simplified version as long as I'm not plugging in 2, which is fine. So if we can do simpler things, that's good. So that's going to give us 4/3. So as a decimal, it's about 1.3 as our y-intercept. To find the x-intercept, we have to be a little bit careful. Okay, we can't use the original. We have to use the factored form because 2 is not going to be an x-intercept. It's actually going to be a whole. Okay, so the top, we're only going to use the x minus 4 when we're finding our x-intercept. And so we're going to have an x-intercept at 4. 4, 0. Okay. We do have a hole. The hole is going to be when x is equal to 2. If I wanted to find the y value, you saw at the very beginning of the video, I went ahead and plugged in what x couldn't be into the simplified version. And so the idea is you take values very close to 2 to kind of get an idea where that hole is. Okay. So if you want to find the y value, you just plug it in. And that is going to be 2. So we're going to have a hole at 2, 2. The vertical asymptote is after we factor and reduce, so we're looking at x minus 4 over x minus 3. The denominator is x minus 3, and the root of that is 3, so vertical asymptote of 3. Horizontal asymptote is we have a tie in degree, we have x squared over x squared, leading coefficients are both 1. So y is equal to 1. Because we have a horizontal asymptote, that means we do not have an oblique asymptote or slant asymptote. And so you would say D and E. Okay, so let's put all that information in. Okay, so we got vertical asymptote at 3. And we have a horizontal asymptote of y equals 1. And let's see, x-intercept at 0, 1.3, and I'm sorry, y-intercept is 0, 1.3, x-intercept at 4 and 0, okay, and also a hole at 2, 2. Now the graph is either going to be like this or like this on the right-hand side, or on the right-hand side, you're the left-hand side. I got some points here, so it's going to be the upper branch. And then on the other side, it's either above or below. And because I got that x-intercept right there, I have enough information to do the graph here. Okay, so go ahead and put that in. All right, there we go. There's our graph with its hole. I think I graphed this one also in Desmos to show you what it looks like. Maybe you're using Desmos to check what your graphs look like, see if you're doing them correctly. And so here's what it looks like, and the application is called Desmos. It is DESMOS, and it's a website, or it's a free application on both the iPhone and Android platforms. Now, if I don't, you see my cursor is pointing to 2 and undefined right there, so there's my hole. If I don't put my cursor over there, it's going to be a solid line, solid part of the graph there, and you won't be able to see anything there. And if you're using like a graphing calculator, like a TI-84 or something to that effect, you will not see that hole in the graph. It is there, but you won't see it. And the Desmos is pretty nice. You can put your cursor over where you think the hole is, and you can actually see it. Okay, I believe that's it. Let's see if we got it. Okay, so here's that again, that table at the end, and it's just replaying the animation that I had pre-written there. Okay, so that is I would consider this a fairly brief introduction to rational functions. Again, this is more for college algebra, and I think we're about done. So we'll see you next time.